The previous presentation, Part 14 of the Fine Art of Fire, was the conclusion in regards to crucible fusion. If you followed my presentations from Part 1 to Part 14, you should be able to conduct a successful fusion which would result in the collection of all your precious and noble metals in a lead button with some degree of accuracy and a slag that contains all the gangue material. In this presentation, I will be discussing an alternate method to the fusion process. This alternate process is referred to as scorification. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. Scorification is an oxidizing method for the collection of the precious and noble metals. Oxygen in the atmosphere is used to oxidize the lead into lead oxide, which in turn forms the fluid slag with any silica which may be present in the ore or concentrate. Any remaining lead will form the lead button which would trap the precious and noble metals, specifically any gold or silver. What is achieved is a 28-gram button containing all the precious and noble metals and a slag which contains all that gangue material that is unwanted. Scorification is the simplest and may be the cheapest method for collecting gold and silver from your ore samples or concentrates. This may include some of the platinum group metals as well. During a crucible fusion process, your resulting lead buttons may be too large, or they may be too contaminated for cupellation. Scorification can be used to further reduce the lead by removing or trapping the contaminants in the resulting slag. If you have any solutions containing gold or silver, scorification can be used as a method of collection and separation, a wet-dry process. As with any process, the ore concentrate has to be suitable for the method to be used. Ore that contains sulfides or silicates can be easily processed using scorification, especially those that contain contaminants such as antimony and arsenic, which are easily oxidized and readily slagged. After a crucible fusion and separation from the slag, you may find a copper matte. These can be easily processed and any trapped precious metals can be separated. Same with spice. Copper and lead bullion can be assayed as well as small amounts of metallics, which results from the sampling of gold-bearing ore. At times, during a sloppy crucible fusion, lead buttons may contain varying amounts of contaminants, or they may become too large for cupellation. If the ore contains antimony, you may want to increase the size of your lead buttons during crucible fusion. Scorification is used to treat these lead buttons. On the flip side, if your samples require oxidation, that is those that are of pure metal or do not contain sulfides, these ores are not suitable for scorification. Any sample low in silver content is not suitable, as well as those that are high oxide ores. High oxide ore or concentrates require the reducing capabilities of a crucible fusion. Like everything else, there is good news and there is bad news. The advantage of using the scorification method is that it's simple in process. It's inexpensive due to the lesser flux material required, and it's quick. But there is a drawback. Smaller sample sizes makes this process less efficient as sample size is restricted. This also makes it less accurate for concentration determination of your source material. Therefore, it is not recommended for the estimation of concentration of precious metals. It is mainly used for the pre-collection and refinement of the precious metals in small-scaled samples, usually used for discovery, and lead button treatment of beads from crucible fusions. The first item that you will need is oxygen. This component is in our atmosphere. It will be needed for the oxidizing process. You will need a muffle furnace of some kind. For an accurate temperature, a furnace kit can be purchased for around $7,000. You can also use a small pot furnace for around $400 or less. The important thing about these furnaces is that the outside atmosphere must be allowed to enter the furnace in a controlled fashion. Also required is a method of temperature control. With a pot furnace, if it is not equipped with a pyrometer, you will need to use a handheld unit or use a color temperature chart and monitor the temperature manually and/or visually. A set of scorifying dishes are required. These shallow, circular, thick fireclay dishes range in size. Most commonly used range between 2 to 4 inches in diameter. Borax is required along with test lead. Now, test lead comes in two flavors, granulated and in sheets. Both must be silver-free. The granulated form is most often used. The lead is used as a collector as well as the oxidized part forming the lead oxide during fusion, which in turn forms a fluid slag component and aids in the dissolving of any base oxides. The borax is used to further aid in the production of the fluid slag. The silica would normally not be required, however. If the sample does not contain silica, then a small amount will be added. It is used to slag off any excess lead oxide, as lead oxide will attack the scorifying dish. After your concentrate or sample has been pulverized to 100 mesh, it must be thoroughly mixed with the flux material that is added. If it is not done, the scorification will fail. It is then placed into a furnace at 850 degrees centigrade for 5 to 10 minutes with the door closed, and any inlet to the outside air must be closed off. During this initial step, the lead should start to melt without oxidizing. After the initial 5 to 10 minutes, the outside air is allowed to slowly enter and the temperature raised to 900 degrees centigrade. This is the roasting stage. It is during this stage that any antimonides, arsenides, and sulfides are oxidized and expunged. Sulfides can be seen as floating on top of the melt. The elemental lead will start to form lead oxide. When the roasting stage is decided as being completed, the temperature is further increased to 950 degrees centigrade and maintained. During this fusion state, any remaining undecomposed material will start to fuse and disappear. Any silver, gold, and if present, any PGM group metals will be collected in the remaining elemental lead. The slag will start to form a wide ring around the molten lead button in the center of the dish. It is at this point the scorification process begins. All the base metals shown from zinc to antimony will oxidize first, in the order shown. Then the lead starts to oxidize into lead oxide. All those shown starting with the arsenic down to the copper will oxidize last. These contaminants, some may still get trapped in the lead. Therefore, for full removal, a second scorification will be necessary. If all goes well, at the end of the process, a 28-gram button containing the gold and silver as well as any PGM group metals, if present, will be the final product once the melt has been poured into an iron mold for cooling and separation. After the melt has been poured and the button separated, if it is brittle, it must be rescorified. On the other hand, if the button appears to be nice and ductile, it can then be compelled, then parted. The flux material required is rather small in quantities and type. The scorifying dishes are small in comparison to crucibles and therefore do not allow for larger gram size samples. That equates to 1.45 to 2.92 grams. Lead, therefore, may be estimated to be 10 grams for every 1.45 grams of material. The borax may be estimated at 1 gram for every 1.45 grams of sample. Silica, in most cases, will not be required unless your sample or concentrate does not contain silica. Copper matte is a good example where silica will be required. This may also be estimated and some experimentation may be needed. The amount of silica that may be needed for 0.01 to 0.05 grams of material may be 1 gram. For 0.05 to 0.10 grams, 1.4 grams of silica may be needed. For 1.10 to 0.15 grams of sample, 1.6 grams may be required. From 0.15 to 0.20 grams, 1.8 grams may be necessary, and for 0.20 to 0.25 grams, one may need 2.0 grams of silica. The slag color will often than not be an indication of what may be the base metal in the sample process. Other base metals that may be present may not show up, as they could be obscured. Notice that the copper usually shows up as being anywhere from light green to a darker green. However, if there's a significant concentration of iron mixed in, the copper green color could very well show up as black. A greenish black color may signify a mix of copper and iron. Some conditions are a little more noticeable, such as nickel and tellurium. Tellurium displays itself as a dark stain on the bottom of a scorifier. During scorification, failures of one type or another may and do at times occur. Most are human error of some type or another. Spitting is quite common, similar to rapidly boiling water. Gaseous trap will violently erupt at the surface, causing material to splatter in all directions. This will happen if your scorifiers are damp. They need to be stored in a clean, warm, and dry environment. At the start of the process, if air is added too quickly, rapid oxidation will cause a quick release of vapors, especially if zinc is involved. This can also happen, and it does, if your initial temperatures are too high. The resulting release of gases can and will be too rapid. Sulfur will oxidize to sulfur dioxide, and carbonates will produce carbon dioxide, and any moisture will turn to steam. Any carbonate ores will have a big effect. If your sample is not properly prepared and your flux is not fully mixed with the sample, some material may be left in the bottom of your scorifier undissolved. I discussed shotting in a previous presentation. You may have lead globules stuck in your slag. This can and does happen if your slag cools too quickly, or is too cool, or slow, careless pouring into a cone mold. The other reason is that there may be a significant amount of nickel oxide in the slag. If you find that your slag is not fully melting and is not fluid-like, add a little more borax, or the temperature may be too low for fusion. Scoria is something that is not wanted. It is usually caused by a large quantity of base metal oxides. It is best to add extra silica. If the temperature are too high, any copper will not be removed completely, and a second scorification will need to be done. The result will be a brittle button that will not satisfactorily compel later. If your material contains arsenic or antimony, a higher temperature will volatilize these impurities if the muffled door is kept closed, inhibiting the oxidation process during the melting period. Silver loss does occur due to oxidation. The longer the scorification process, the more will be the silver loss. This can be mitigated by ensuring that the liquefaction of the sample is thorough. This will allow the lead to reduce the silver and therefore be collected in the lead button. I mentioned that scorification can be accomplished with wet samples, that is, gold and silver bearing solutions. Some of you miners and or prospectors may also be trying to recover these precious metals from scrap, such as jewelry or electronic components. You are also probably using aqua regia to dissolve these metals. Well, after neutralizing the solution, let it evaporate until the residue is perfectly dry. and this can be made or done by heating it to 100 degrees centigrade. Once dried, pulverize to a powder. What you want to do is place the solution into or onto a tray lined with a lead sheet, after which the residue can be scraped off. The foil can be cut and folded into cubes, and the residue placed into each cube for scorification. If you want to save the silver, the gold should be precipitated first, filtered, washed, and dried, then mixed with the granulated lead and borax to be scorified. The remaining solution to be evaporated for the silver, then mixed and scorified. On the other hand, you can add your solution to 60 grams of lead oxide, which is placed on an evaporating dish or tray. Let it evaporate and bake at 100 degrees centigrade until perfectly dry. Mix it thoroughly with the required suitable flux material and conduct a crucible fusion. This presentation concludes the first segment of the Fine Art of Fire. If you have been following along from presentation 1 to now, you should be able to conduct your own fusions for the pre-collection of your precious and noble metals using crucible fusion or scorification. You should be able to produce your own lead buttons, but what do you do with them? They still need to be further refined. In the next presentation, I will be introducing and discussing the second method in the fire assay process, cupellation. If you found this presentation of interest or know of someone who may benefit from this information, please do give it a thumbs up, a like, and a share. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.